McKinley, and I chose today to give you a lecture that covers about 25 years of my career and some of the history of memory management. And so instead of more learning some specific technical work, I'm going to talk about both, although you will hopefully learn some technical details about garbage collection, but I'm framing this around how decades of research evolves and how you can help yourself in your career by building software engineering systems that are easy to extend so that you can innovate faster and better, and you can compare with different approaches more easily. And most of this work has been done with Steve Blackburn, who was my postdoc at the University of Massachusetts in 1999. We published our first paper together in 2000, and we just got one paper accepted at UPSLA. We're very excited on garbage collection, and another one conditionally accepted with major revisions, so we hope to get that one in too. But as you start your careers, you can choose who you work with. And Steve and I, even though we've lived on other continents for most of our collaboration, have had a very productive collaboration, and of course you build deep friendships over those times as well. And think about who you want to be with and who you want to work with, because it can give you a lot of joy. Of course, there's, like every relationship, it has its ups and downs, but persisting in this collaboration has been super productive for both of us. And then one of the key contributions that is the conditionally accepted paper is with Wen Yu Zhao, who's at ANU as a PhD student, and he's about to graduate, so I want to acknowledge them as my collaborators. So what I'm going to do today is give you a garbage collection design and implementation through the lens of breaking the space-time trade-off and focusing on memory performance and mutator performance. When a garbage collector person says mutator performance, that's the program. And you can stop the world and run the garbage collector, and that I'm going to focus on that in the beginning of this talk. Or you can do things concurrently while the program is running. And those things that you're doing together while the program is running is harder to measure. So I'll start with taking the mutator on its own, and then the stop the world part of the garbage collector and thinking about that. And so one of our first contributions was IMIX mark region collector that uses lines and blocks that mimics the lines and blocks in a cache and memory hierarchy, and that's for a reason. And that helps you try Gemini. Got it. I've been doing that, as you can imagine, at Google now. And then the next major contribution I'm going to talk about is LXR, which was how you think about short pauses versus low latency in applications. And then I'm going to tell you how we built, and now Steve has rebuilt in OpenJDK a memory management toolkit that all of you can use if I inspire you to do garbage collection research. And the structure of that, and the new abstraction called work packets that we built all our GCs on top of, and some major advantages of that abstraction. And then all this work was built on benchmarks, performance methodologies, and more methodology. Every paper we write, almost, requires some interesting new methodologies. And so I could give a whole talk on that. If you've heard of or used the Da Capo benchmarks, those started with our an early project that we did on Java performance optimization while I was at UMass and at the University of Texas. And I love that area, but I'm not going to focus on it today. So that's the overview of what we're doing. So why should you care about garbage collection? Well, programming language that people use rely on garbage collection. And you might find it hard to believe, but in 1999, when we decided to work on optimizing Java, that was risky. Okay? Because lots of people weren't using Java at that point. But the programming language benefits for productivity, for making humans program better, it was always very important for many applications and many new companies. And so more and more programs got written in Java, and then language innovation isn't stopping. And many of the other speakers today are talking about the mathematical foundations of programming languages and how to basically make them better, easier to prove things about, easier to write correctly, easier to get Gemini to generate code correctly for. So so we're not stopping on that journey. And for example, the Go language at Google, the Rust language that really makes it a lot harder to have concurrency bugs. These things get adopted at a very slow pace, but betting on them early in your career can help you a lot as a life lesson. All right, so that's why you should care about garbage collection, because more and more languages are using it, and not only that, languages will evolve and they'll continue to use garbage collection for its programming language benefits and for proving things correct. All right, then why should you care about performance? And in compilers and runtime systems, you are the middle layer between programming language and application innovation, hardware innovation, instruction set, expression of that hardware. And so things aren't standing still. And in fact, right now, that I was very surprised to see nobody had AI in any of their titles of their talks here. So you are at the beginning of a fourth revolution in computer science and in technology and innovation, and nobody knows what's going to happen. All right? But we have a new tool. It's super powerful. People want to use it responsibly. People want to learn on data that they should be allowed to learn on. It's a very complicated space. So there are going to be new applications. There are going to be new programming languages for that. I hope we evolve past Python. But that's a big thing that's going on right now, as you all know. So in the glue, it determines performance. And the better your performance, the lower your cost for your application, the more likely it is as a company that you can make money and invent something new and make it powerful. So the runtime has a garbage collector in it. It determines the layout in memory. It determines how well the program can use parallelism. And if you don't get it right, your programming language will perform poorly and you'll be unhappy if you're paying for cloud services. I work in Google Cloud now. That garbage collection is now my hobby. All right, so I want to remind you of what the parallel hardware kind of looks like right now. So there are lots of CPUs on the chips. They're attached to L1 and L2 caches. Why is the L1 cache smaller? Because you want lower latency access to it. So there's a great paper by Mark Hill why you really want one cycle access, but today most caches are about 3 to 20 cycles of latency to access that memory, and then bigger caches take more latency to access, and memory with NUMA is organized in blobs around a chip so that the latency is also reasonable. We sell at Google Cloud we have a lot of customers who want more memory per CPU, that they're able to drive their applications and need more memory. And so some of them use local SSD or non-volatile memory to store even more, so that the DRAM is a cache of an even bigger application storage-wise. And yet they're doing things like compression and everything else at all the different layers. So that's the memory hierarchy. So in order to get good performance, you have to be hitting in that L1, L2 cache a lot, otherwise you're waiting for memory longer and longer. All right, so that's the architecture context. And as a compiler and runtime person, you should always be thinking about that context. And that context, if you think about my career, that was the context I wanted to work in. But the context I got was the run up to you at the early part of my career. And I worked on parallelism. And then all the parallel computing companies went out of business. And Intel and ARM produced single processor chips that were so fast that every generation was getting faster and faster, and so everybody focused just on one little CPU, and one or two layers of the memory hierarchy. So we went from that to really having that, even though people knew we would get here eventually, it took a while. So being right early doesn't help you, but then you can be prepared. All right, so the historical foundation of garbage collection goes back to 1960, in the McCarthy era. Also, McCarthy invented the Mark Sweep garbage collector. And it is both a heap organization on where you put objects, and it included a tracing algorithm, which I'll talk about in more detail. And then because of how the heap is organized, the allocator has to work in a certain way, all right? And then that had its issues. And then Steiger in 1967 said, memory is the most important resource, okay? We don't have very much memory. So what we want to do is squish the live memory as much as possible into the smallest possible space, and we're willing to spend more computational time to do that. So the heap was organized so that all the objects are next to each other, and you allocate, it's called a bump pointer allocator, and you smooth them out, and then you squish them together, and I'll show you that in more detail. And that's 1967. And then in 1969, instead of mark compact, where you have to take multiple passes, Semispace says, maybe we're going to have a little bit more memory. So you take half the memory and you allocate into it, and then because all those objects might survive, you copy them in. So you spend less time, and you have double the space, okay? And then heap organization basically does not change until 40 years later, until the mark region, a collector that Steve and I present at PLDI in 2008. So basically a decade of innovation in heap organization, and then over 40 years or about 40 years where nothing happens, all right? That's a big gap. All right? So, and why, I'll get to much later how that happens. Okay. We have extra roots right now. Roots are important. So when you start the garbage collection, you have to find the pointers into the heap. Those are in the stacks and registers, and those are called roots. But that wasn't the order I meant to go in. So we have three fundamentals of the garbage collector. We have an allocator, we have the way we identify what's live or dead, and then we have the reclamation policy that says how we go find the dead stuff and get it reclaimed so we can allocate into it again. So the two allocation frameworks that work for all the collectors, the the really old ones, and IMICs are free list and bump pointer allocation. So a free list allocator has groups of objects organized by their sizes, called size classes. All right? And why do you do that? Because otherwise you have to search too long to allocate. So you can build a size class allocator that would bump point and then goes and tries to figure out where I can fit an object of some size, but it's really expensive to allocate. So instead, every block has a size. You go, every block is identified by if it has any free space in it, and so you can quickly look up the right size class based on the object size and go allocate into it. All right? So that's the size free list with a size class allocator. Bump pointer says just put the objects in a row in a sequential buffer and wait until you run out, and then you can't allocate anymore and you have to trigger a collection. In the free list allocator at the top, when you collect is not when you've completely run out of memory, but when all the blocks are assigned a size class and one of the blocks runs out of memory. So there's some additional fragmentation there that you don't get in the bump pointer allocator. And when the objects get allocated in time and they're next to each other, they're often used together in time because they were allocated together in time. But in the free list organization, they're now spread around and they might not be on the same cache line or in the same they might not be together in space, but they were accessed together in time. All right. Then you need to identify, and that's when the roots were actually supposed to appear. so then you need to identify what's live in the heap. And there are two basic ways to do that. Tracing, which implicitly identifies what's dead by identifying what's live. So you start at the roots, what's stored in the, you have to reach a pause point, dump what's in a register, and look at everything in the stack that's pointing into the heap. And those are your roots. And then you perform a transitive closure over the object graph. And here I'm showing a very simple transitive closure where you point at that root object, and then you go and you mark it. My marked bit is missing, but you can see my marked bit in the other object where I have marked it. So those little round dots, that means that object is alive and I've marked it. And I'm going to use that throughout the rest of the talk. All right. For reference counting, you do something different. All right. You still have to scan the roots, because if you reference count every register usage and every stack change, it's too expensive. So you still scan the roots to get the initial pointers into the heap, and you increment those, and then you later say, so those objects are permanently live. You put a corresponding deck. So when you scan the roots, every root you go add 1 to, you say, oh, later I'm going to do a deck at the beginning of the next collection, and so you put in a buffer the previous roots all with a deck in it. So then on the next GC, you go through your roots, you increment everything, and then you apply all your decks. So the roots, if a root changed and an object is now dead, you can identify them. All right? And you count, right? And there are a bunch of optimizations on counting that I'm not going to talk about today. Yes? Could you say your name?
I'm Ricardo. I'm also I was wondering what a DAC is.
A decrement.
Oh, a decrement.
So increments, inks, and decks. Increments and decrements.
Thank you.
You're welcome. Sorry. All right. Any questions on the basics here? What's your name?
Steven. You talked about kind of investing in languages early and this kind of thing. I'm wondering if the techniques we're talking about are maybe if they're broadly applicable to every garbage collection opportunity, or if they're something specific to the JVM.
These are the underpinnings of every garbage collection. So there are some language characteristics that make choices of underlying collectors more or less difficult. So, for example, pinning is supported in Ruby, and so if you have pinning, you can't really use a bump pointer because you can't empty out the whole space unless you do something like IMIX. And Steve has a paper, and we have an old paper on incorporating pinning into a bump pointer allocator, but you have to have something like IMIX, which I'm not there yet, okay? So the choice of language, if it has pinning, requires put some additional restrictions on the garbage collector. But if you can identify all the pointers to everything, and you can do some amount of copying, you can use any of these allocation or identification mechanisms, but it will have impact on the heap organization, which I'm about to get to. Your name? Dustin.
Just wanted to ask, this may be speaking in blue, because it may not be basics. I want to know when you briefly describe the trade-offs of the identification with respect to cycles.
That's right. So a limitation of reference counting is it can't find cycles, so you need a backup tracer to go find it. So reference counting is not a complete collector, so it requires some tracing as well. But the advantage of reference counting is it's immediate. So you can, and some people have built this, reference counters that as soon as the object's dead, you identify it because you're doing you're keeping everything up to date. But the expense of that is usually too much. So just like you need to pause every once in a while when you run out of memory and do a collection, you need to pause and do some reference counting. But you can to get better immediacy, you can reduce the time between pauses and get quicker, more short pauses, and I'll talk about that in the LXR collector. Good question. Yes, reference counting can't get cycles. Important limitation. All right. Now, reclamation is what makes the heap structures different and have big implications for the algorithms that work on top of it. So a sweep to free says once you've either identified the dead objects or the live objects in a free list, you can do reference counting or tracing on a free list. All right? And so when you're finished, you have some live objects in your size classes and some dead ones, and you either, after your trace, you go through and know all the objects that weren't marked, and so that's a sweep through the free space to identify the dead objects after you mark them. Or if you've done reference counting, then you similarly need something to tell you that all the 0 ones, sweep through, find all the 0 ones, and put them back on the free list for that size class. So you can use either a tracing or reference counting to sweep the dead objects to a free list. All right. For compaction, though, you can't really, well, you could use a free list, but it makes less sense. All right? Like, you could mix and match. But here, for compaction, what you do is you have these objects. I'm showing essentially those 2 objects being live, and they were over on the right-hand side of the heap, and now you want to push them all the way over to the left-hand side of the heap and squish them together and get rid of the dead space between them so you can bug point in the rest. In order to do that, you first have to find all the live objects, because if you start copying those objects and you later find that the first object on the left-hand side was live, you will have copied over it. So you have to do a pass to identify all the live objects, and then you have to do another pass to figure out where to put the objects, and then you have to put them in, okay? So that's more computationally expensive, but at the end, you have the very tightest heap you can possibly have with all those objects put together. And then The evacuation says, let's just, every time we see the object is live from the root, we're going to move it, we're going to copy it into another space. And you'll notice that the object order has switched here. So usually in compaction, you keep the objects in their allocation order for a variety of reasons. Like you don't have to, but you do. But for evacuation, you want to copy the object as when you mark it and identify that it's live, that's the time to copy it, because then you get one pass of both marking and copying, and so that's faster and more efficient. All right? And then sweep to region shows that I've broken that space up into two larger regions, and I get to reclaim one of those regions because there are no live objects on it, but the other region has some fragmentation in it because I've identified those live objects and I haven't moved them, so that region is partially free, depending on how I organize it later. You'll learn about that. And and one of the regions is completely free. Any questions on these components of the algorithm?
I have a couple questions.
What's your name?
Luis. So the first question is in the evacuate diagram. I was trying to figure out how to read that diagram. So at the top we have those objects are live.
Right.
And then at the bottom we sort of
That's after we copied them.
copy.
So when we visit, see the root object to the small one in the tracer, okay? When you follow that root, you say, oh, that object's live. So I mark it live and I copy it and I put what's called a forwarding pointer in that object. All right? And that forwarding pointer says if anybody else points to me, they'll see I'm already forwarded and they can update my new, they can update the pointer to that object with the forwarding pointer.
Okay.
Okay?
Does it remain live in that new region?
Then the unshown is after I copy it, I get the whole top region back as empty.
Okay.
This is like right before I reclaim the whole empty space at the top. Any other questions, Elise?
The second one was, we definitely just really quickly, like a high level, you gave it earlier, I kind of lost it, a high level view of like what each allocation, identification, reclamation are.
So allocation is the programmer says new. So you have to put the object somewhere, okay? Identification is I've decided it's time to collect, either because I ran out of heap space or I want to keep my pauses short and do a little bit of work right now for a variety of different reasons. And so I've started a garbage collection, okay? And so then you have to identify the objects through these one of these two mechanisms that you think are dead. And then reclaiming is I now know where the dead stuff is, and I can identify completely empty free memory that I can now use. All right? And that's when I can allocate into it again.
I was wondering if all possible combinations of these three options are valid?
Yeah, they are. But some of them have never been instantiated, but they are all valid.
Maybe I just missed something, but can you explain again, perhaps, how you can ensure that sweep to region doesn't just fill up with like small live objects across all the regions, which like. That's Steve's team just wrote a worst case program to exactly do that. Because what you can do is every size, so you could essentially make all objects small, fill up the whole heap if you're given a fixed size heap, and then free all but one of them on each of the blocks, and then allocate a large object. You're out of memory, you fragmented your whole heap. Okay? Most programs don't work like that, but the free list does have some pathologies that are underappreciated, and some Perry Chang, David Bacon, and I've forgotten who else is on this paper, did compacting sweep to free. So if you had too many of those, they did the copying of the objects all onto the same size class bin to get completely free blocks that then could be assigned to other size classes. And we use an optimization like that in Immix as well, which I'll show in a minute.
Cool.
Good question. What was your name?
Sam.
Sam?
Yes.
Samuel?
Just Sam.
Sam. And who was over here who didn't tell me their name? In the back, you can tell me your name.
Ty?
Do you have a question, Tom?
Oh, no, sorry. I thought you were asking me what my name was.
You looked like you wanted to tell me. All right. So now we're going to go back to these 4 algorithms, and we're going to, for each of these 4 algorithms, we're going to mix and match what we just learned about allocation, and we're going to focus on tracing for simplicity of exposition. Okay? So now, so I don't have to run through my animations. Let's look at Mark Sweep. Okay, so the Mark Sweep algorithm uses the free list as allocation. It uses tracing to identify what's live and what's dead, although I should have put the tracer on top of the heap shape. I spent lots of time on these slides and I gave up on that part. All right, and so then once I'm done tracing, then I can sweep to the free list. In the example I've shown, I filled up the middle class size, okay? That triggered a GC because I had another allocation of that class size and I didn't have anywhere to put it. Even though I had enough free memory for it up in that top block is assigned to larger size classes, so I can't use it for the smaller size class. Although there's a very interesting paper by Doug Lee on how to do some of that. That compaction and resizing things. So it's not impossible to do that, but it just becomes more and more costly at allocation time. So as all the production collectors that use a free list aren't doing that. They're using this organization. And those collectors, so the C and C++ collectors use free lists like this, and the old space collectors for production, JVM, and other languages use a free list, like Go uses a free list in its garbage collector. All right? So they're subject to, I have some fragmentation now when I allocate that extra small object, but now I get some of it back over here, and I can reassign that completely empty block to whatever size class I want. All right? I've shown it with the 2 empty big objects, but after everything's